BC Calculus, Lesson 7.2, Antidifferentiation by Substitution. So now that I know how to pronounce things, we get into what I did first when I was taking calculus, integrals that aren't definite. And I believe that the reason it's taught in the way it is now is to make sure you're clear the definite integral means something. It's a number. The indefinite integral means a family of graphs. So I've got the whole definition written here, and it's just basically anti-differentiation with a bunch of specific cases you have to be aware of. Remember, this is the integrand. And this is the integral sign. This is the variable of integration, which can still be a dummy variable sometimes, but we'll get to that. So, straight up antiderivative. The rule is add 1 and divide by it. The derivative of negative sign is cosine of x, and we slap our little plus c out here. So go back and check, 3x squared over 3, 3's cancel, yep, cosine negative, yep. And that's how I do integrals. Write them out and check them. Here's some of the properties. I can take the variable and shove it out front. I can break a plus minus up into two different integrals, which is important for our next lesson. This is the formula I've been waiting to see for quite some time for antiderivatives. Add 1 and then divide by it. Don't forget your c. N cannot equal, thought I fixed that, negative 1, because this is when we have a negative power. It's natural log. Don't forget your absolute values, because it doesn't work otherwise. Trig formulas going forwards and backwards, same thing. Exponential and logarithmic, same thing. Only difference is this. We'll come back to that when we do integration by parts. And this one, of course, won't pop up very much today, but be aware. So verify the antiderivatives. Well, this is dumb because the derivative with respect to x of the natural log of u plus c is just 1 over u. So integral of 1 over u works. And the derivative, this one actually makes a little more sense. U ln of u minus u plus c. Chain rule it. U times 1 over u plus derivative is 1 times, leave it, ln of u, minus 1, and the constant vanishes. We get 1 plus ln of u minus 1 equals ln of u. That's about it. I haven't memorized that formula yet, but I intend to. Pay close attention to the dx and the du. People confuse them all the time and just kind of let them wash through. Find the integral of f of x dx. So here's f of x. Integral of x to the third plus 1 with respect to x is x to the fourth over 4 plus x plus c. Now we do the next one, integral of f of u du. Integral of f of u, keep putting little f on my integral signs, with respect to u, well that's the integral of u is x squared, so f of x squared is x squared to the third plus 1. Let's do this differently. just put in u, f of u du. So that's the integral of u to the third plus 1 du, which is u to the fourth over 4 plus u plus c, which we have to change a little bit because we got to plug in our x. So it's x squared to the fourth is x to the eighth over 4 plus x squared plus c. A little different than the one we had before. And then when we get confusing, integral f of u dx. So integral of f of x squared dx, because that's what u is, which is the integral of x to the sixth plus 1 with respect to x, which is x to the seventh over 7 plus x plus c. So like I said, just be careful. And substitution, which I have not taught yet, so I'm looking forward to it. We always use the letter u, and the trick is, what do we use to substitute? And in this case, it seems obvious, but you never know. You say u equals cosine of x, because that's what's up in the exponent. When I take the derivative, it's going to get chain ruled. And then we take the derivative with respect to x, leave it up top, and then we sub it in. So we have sine of x dx, integral of e to the u du, which is just e to the u plus c. Sub that back in, e to the cosine of x plus c. Tricky, tricky. Pay attention closely. Try another one. U equals 5 plus 2x to the third. Du equals 6x squared dx. I am going to divide both sides by 6 because I only see an x squared and a dx. I want to sub it in nice and clean. Du over 6 equals x squared dx. Change what's under the radical, just u. Change the x squared dx to du over 6. I like to rewrite things, u to the 1/2 over 6 du, which is, add 1, get u to the 3/2, divide by 3/2, which is like multiplying by 2 over 3, still got the 6 there, a little canceling, don't forget your plus c. Sub back in for u, 5 plus 2x to the third, to the 3/2 over 9 plus c. Now, this is something I've done well in my past, but I remember quite clearly, so I'm going quick. Watch out. It's very doable. It takes a little getting used to. You see how the chain rule works, and we're trying to undo it with this substitution thing. But it's hard. I hadn't seen this in a long time, so I came up to it and said, geez, I have no idea what to do with it. So I was like, cosine of 7x over sine of 7x dx. I could do a natural log of sine of 7x. So let's try subbing that. And there is a lot of guess and check here. And for the first time, I believe you will have to actually work hard. So derivative, boy, that was painful. Derivative of sine of x is cosine of 7x plus the inside. I don't see 7 over here, so I'm going to divide it out. I do see cosine of 7 dx, so I can go 1, well, we'll just put the du on top. Du over 7u, which equals natural log of u over 7 plus c, which we change to natural log of sine of 7x over 7 plus c. This is right now going a little bit too well, so I really don't want to screw up. Made a small mistake. Remember, when we take a natural log, we have to put an absolute value. Oops. But, you get the idea. Neat one here. Cosine squared of 2x. Did not know what to do on this. Realized after a minute or two, hey, that's just secant squared 2x dx. So this makes it a lot easier. Integral of secant squared u du is tangent of u plus c tangent of 2x over 2 plus c. So a little trig work there, and it's not that hard. You just have to see it. If you haven't seen it before, it's very befuddling, to put it mildly. Cotangent squared. Maybe there's an identity I know of. Cosecant squared x minus 1 equals cotangent squared x. Yes, this might come in handy. Integral cosecant squared 3x. This was just the identity I was basing it off of. Need to put what's really in there. Minus 1 dx. Why would that help us? I don't know. Let's go find out. U equals 3x. I have a lot of spacing issues when I do these problems, so watch out. Du over 3 equals dx. Integral of cosecant squared u minus 1 du over 3 equals cosecant squared is negative cotangent u minus u plus c. This whole thing's over 3. Now I'll just put it both. Equals negative cotangent 3x over 3 minus 3x over 3, which I'm going to cancel on the spot. How did I do? Hey, look at that. I got it right. I'm checking my answer key. Pretty cool. Cosine to the third x. I think I know what I'm going to do with this. Yeah, I'm going to go say sine squared x plus cosine squared x equals 1. I'm going to get cosine squared x equals 1 minus sine squared x. And I'm going to break this into cosine of x, 1 minus sine squared x dx. I'm guessing I need to sub u as 1 minus sine squared x. No, that won't work, will it? Yeah, I don't need all of it. I just need u equals sine squared x. No, just sine of x. Then du equals cosine of x dx. And I can just sub that out. Man, it's weird how well these work sometimes, and other times you're just staring at them for hours. 1 minus u squared du. This equals u minus u to the third over 3 plus c, which equals negative cosine to the third x over 3 plus cosine of x plus c. Goodness gracious, I can't sub in a sine to save my life. That was almost embarrassing. Sine. Yeah, there we go. So as you can see, it's actually a significant amount of work for the first time in a long time. What about definite integrals? can we use substitution to solve those? Because we got our little calculator because it's a thing, but wouldn't it be nice if we had yet another tool in our backpack in case, oh, I don't know, we had a AP exam that had large chunks without calculators. And we can be really clever with this limits here, which is really, really cool, actually. Kind of like this stuff. I'm such a geek. Let's start with u equals tangent of x and see where that takes us. Du equals secant squared x dx, and that looks very nice. But now I'm going to sub in for u, and I could back it out and do all the substitution, but we also have this little trick. U of 0, if u is tangent of x, u of 0 equals 0, and u of pi over 3, tangent of pi over 3 is sine of pi over 3 over cosine of pi over 3 is root 3 over 2 over 1 half is root 3. Not trusting myself, I should probably check that on my calculator. Yeah, I got lucky. So we change this whole thing. 0 to root 3. Tangent of x is u. Secant squared x dx is du. Isn't that cool? U squared over 2. Hey, what happened to my c? This is a definite integral. I've got to evaluate it. And I don't have to sub back in, which is really, really nice. 3 over 2 minus 0, 3 over 2. And I can check it with a calculator, which is nice. And yes, last one. Long video. So u equals x squared minus 4. Du equals 2x dx. I'm going to have to divide by 2. Du over 2 equals x dx, which is fine. And then u of 0 equals negative 4. That might be a problem in our near future. U of 1 equals negative 3. Rewrite negative 4 to negative 3. Du over 2u equals natural log absolute value of u over 2 from negative 4 to negative 3. Thank goodness we have that absolute value. Otherwise, we couldn't do this. Natural log of, I'm just going to put it in as 4, minus natural log of 3, because it's absolute value, over 2. I will personally accept that as an answer. Having a rough time speaking today. And I have it backwards. That's bad. Top minus bottom. And you can combine that to 1 half natural log of 3 over 4. I'll accept that as an answer. And you can actually blast it on the calculator if you want. Put a little line over here, keep those separated. And you're lucky because the current AP exam has all this integration stuff. We'll do antidifferentiation by parts. But mostly, and this was substitution, you get to use your calculator to do the definite integral. We have so many great mathematical techniques and so much computing power, we don't have to worry as much as we once did at being super efficient in all types of integration. There'll be a lot of it, but not quite as much. That is it, as in all things. Happy mathing.